So we just looked at how to find the eigenstates and eigenvalues of a Hamiltonian that's a lot like a Hamiltonian that we know the solution to, but has an extra term added on. If that extra term is small and has a small effect, then we can get useful results out of expanding out our eigenstates and eigenvalues in terms of that small parameter and just taking the first few orders, possibly even the first order. So we found the first order change in the energies and the eigenstates, and that's often enough, but sometimes we want either very high precision predictions or the first order terms are actually zero. They give us zero correction to the energy, and that doesn't mean that the energy doesn't change, it just means that the first non-zero term should be the second order. So let's have a look at the second order perturbation. And all we do is we go up to the eigenvalue problem that we first saw, and we expand it out, and we take the second order terms, where you equate the left and the right hand sides. And you can see that we get more terms, and as we go to higher orders, we'll get increasingly large sets of terms. And again, we take the scalar product with a bra on both sides. When we apply H0 back to that, we'll get, and when we take the inner product between EJ0 and EJ0, we just get 1. This term here and this term here are identical, so they cancel. And this term here, we already know what EJ1 is because we calculated it up here, so we can plug that in. And this term here can actually be set to 0 as well, because you can force that the inner product between the unperturbed and the perturbed states is 0. How do you do that? Well, let's go back to here where we were working out what the perturbed states were. If I take this state here, and I were to, and suppose it solves this equation, if I were to add a little bit of the unperturbed state, this EJ0 in there, then what I would get is I would get H0 minus EJ0 acting on my EJ0. So that would be EJ0 minus EJ0. In other words, I would add 0. So I can take EJ1 and I can add or subtract any amount of EJ0 from it, and it still is the first order state. Which is exactly why we don't have to worry about adding the jth state there, because we can assume that that is 0. Another way of thinking about that is if you think of EJ0 as a vector, then all of these corrections must be perpendicular to it. And in fact, we can enforce that. So we can force this to be 0 as well, in which case we have that the second order energies are given by this, and if we expand that out from there, we get this. And there you have it, the second order energies. And we could go on and we could calculate the second order states as well, but we will stop there for now. So provided it makes sense to treat the original perturbation to the Hamiltonian as a perturbation, then we can find out the first order correction to the energies in the states in terms of the unperturbed states and energies, and we can also find the second order correction to the energies in terms of the unperturbed states and energies. And you'll note that all of these required us to have non-degenerate eigenvalues. In other words, they had to have distinct eigenvalues for each state, and we'll talk about how to do degenerate perturbation theory next. I just want to make one extra comment about the fact that the expansion, the Taylor expansion of the states in terms of this small parameter lambda is non-unique. That could concern you, except that any physical quantity that you calculate is of course unique.